talk is about a variation of classical planning, epistemic planning, which is concerned with multi-agent systems, where agents have to not only reason about what they know and what they don't know, but also what other agents that they might be collaborating with know and don't know. Why could we be interested in epistemic planning? There is example applications for human-robot interaction, for example, with our blocks world-building Baxter robot that we have here. Another project that I was involved in is with virtual agents that may interact with humans. And if they have a proper interaction, they also possibly have to reason about what humans know and don't know. And lastly, in computer game playing, there are some interesting games, card games, for instance. The one that is shown here, more prominent, is probably Hanabi, also a game where players have to reason about what other players know and don't know. And in all these cases, they have to make epistemic plans. The paper that I'm going to present introduces two things. First of all, a dynamic epistemic representation language, a new representation language for event models. And I will briefly mention the advantages of this representation language in terms of its efficiency as well as its completeness. And in the second part of this work, we have been looking at how we can model dynamic epistemic reasoning at a pure syntactic level, where we can reason about action sequences with a single and finite epistemic model that represents the state of affairs from the view of all the agents and what they know and don't know. Now, this work, there have been previous works on trying to find a nice representation language for this type of problems. And the closest is probably Baral et al.'s 2015 paper, where they used a particular example that we also put in our paper to illustrate several aspects of dynamic epistemic reasoning and planning. This example has three agents, A, B, C. There is a box that can be opened with a key, and there is a coin inside the box which can either show tails or heads. And then agents can perform different actions. In particular, they can signal to each other to pay attention or distract one another to not pay attention. And then they can obviously open the box, and one agent can peek inside the box to find out whether the coin shows tails or not. And then agents can publicly announce that tail is up. This is a nice scenario because it illustrates a lot of features of dynamic epistemic reasoning. Now, Baral et al., they have developed a language based on action description languages, where they introduced a few language concepts that in particular had to deal with agents that look at each other, that follow an action, or that are distracted and do not follow an action. And we thought of trying to simplify the language even further, so that with the help of just a single language construct, we can express everything that we want to express. And for this purpose, we have been combining the classical signature of action description languages, where we have actions and fluents, plus in a multi-agent system, a set of actions, a set of agents. We have combined this with a new element that was motivated, for example, from hidden Markov models, where you can have states that are hidden to the observer, but these hidden states, they emit observations. And these observations is all that agents need in order to know what they know about a state and what they don't know. And with the help of these observations, we can then specify actions in a dynamic epistemic multi-agent environment with the help of just a single type of law. A causes X if some condition holds. And this X can now be a classical effect that happens, as in classical action description languages, or an observation that is being triggered. So for example, classical effects in the scenario that I showed you, and that is described in detail in our paper, would be, for instance, if agent X distracts agent Y, then an effect would be that agent Y is no longer looking at agent X. This is accompanied with these observational effect laws. For instance, we can see here that if X peeks inside the box, then Y gets the observation that X peeks inside the box if Y is looking at X. There are further observations that can be made in this setting. We completed or complemented these action laws with standard precondition laws. An action A is executable under certain conditions. And I'm showing that here mostly to stress the point that both these conditions as well as these conditions, they can be epistemic formulae. For example, here is all the executability conditions for the example. And take note of the last executability law here, which says that we allow agent X to announce tails only if the agent X does know that tail is true. So these conditions can indeed be arbitrary epistemic formulae. We have then defined a semantics, and for the example that I had on the previous slide, it's going to be a bit too large. So I'm using a much simpler example, a standard example of an agent A flipping a coin, which has the standard physical effect. And here we also have an observational effect. If the agent is looking at what the agent itself is doing, then the agent gets a corresponding observation. And then if you want to define the semantics of this language, you have to look at any consistent combination of these effect conditions. We have 4 effect conditions here. Possible combinations in total are 2 to the power of 4, which is 16. However, of all these combinations, there's only 4 that are actually logically consistent. And each one of them defines a specific way in which this action can play out. And this is why it then gives rise to different events in which the action can happen. And then we say that an agent X cannot distinguish different ways in which this action can play out if the different ways result in the same observation for X. So if we apply this to this example here, then we can represent this representation here. We know that the semantics is given by this so-called event model, which specifies an accessibility relation that corresponds to agents cannot distinguish different ways in which these events occur. We can see that B, because B doesn't get agent B any observation here, B cannot distinguish any of the 4 possible outcomes, and A cannot distinguish tails from not tails if A is not looking, but if A is looking, then these 2 events can be distinguished. So in this way, for any such description, you can map it into a standard classical possible event model. What are advantages of this representation? What I said on the previous slide is each consistent combination of effect conditions determines a separate event. There can be exponentially many such combinations, and that means that in certain cases, we can have an exponentially smaller representation of a given event model. And this in particular can happen if you've got lots of agents that may or may not observe a specific action. On the other hand, we were also able to show that in this language, we can represent every multi-agent as 5 event model, which is the standard class of models that is being used for epistemic planning. And the proof is nice and straightforward because you can give a canonical description of every given event model, where you consider a particular event E, and then you list just all the effects that this particular event might have, plus an observation, and this observation corresponds to the equivalence class or the indistinguishability class for a specific agent. And this representation, this canonical model, is polynomial in the size of the event model. So we get this exponential blow up in one direction, but we don't get this in the other direction. That was the first part of the paper. And now more briefly on the second part of the paper, where we were combining this representation language for the effects of actions in a multi-agent dynamic epistemic setting with a language that allows us to specify actual initial states of a planning problem and to reason about the effects of sequences of actions. And for this purpose, we were resorting to previous work by Burrell et al. That I've already mentioned earlier, but also by Son et al., where we were using a restriction of all possible dynamic epistemic logic formulae that could be used to specify a state in such a way that this becomes manageable. Worthy of note is that even though this is a restriction, it can still express standard benchmark problems such as the muddy children problem. What we have been using, and this was really adopting from previous work, we have been restricting ourselves to initial state descriptions with objective formulae where we say an objective formula is common knowledge, and there is common knowledge about what agents know and what they don't know. And with the help of these formulae, we can, for example, specify initial states in the coin flipping example where objectively the coin shows tails, but no agent does know this. And it is common knowledge that only one agent is actually looking, and this would be agent A. It is implicitly assumed that what is not explicitly known is unknown. So in particular, it is not known whether the coin shows tails or not. What we then can also adopt is a language that allows us to specify information that we can derive about the effect of actions. For example, we can say after flipping the coin, agent A does know that the coin no longer shows tails, whereas B doesn't know this, but B does know, because it's common knowledge that A is looking at the coin, that A knows whether the coin shows tails or not. Then we wanted to combine this initial representation, state representation language, in such a way that when we want to reason about the effects of actions, that we can resort to reasoning with just one single epistemic model. And that proved to be a challenge that Barral et al. Have also looked at earlier. And they came up with, because in general, when we have an epistemic collection of epistemic formulae like these, we can have infinitely many infinite models. So we do need a restriction in terms of what we can further express in terms of so-called finitary theories. And we have a theorem that says for any such finitary theory, there exists an epistemic model that exactly characterizes this particular theory. Now, quickly jumping over this slide, because I can see that I've got only half a minute left. What we then added to this, and again, we were resorting on previous work, is a completion operator that was completing initial state specifications like this by additional formulae that tell us specifically that this is all that we know. And with the help of these additional formulae, we can then resort to one single event, one single epistemic model to represent this particular state. And this brings me to the conclusion, where the paper consisted of two contributions. The first was this dynamic epistemic representation language, a simple, high-level and compact description language for event models in DEL planning, which was provably representationally efficient and, on the other hand, complete for S5 event models. And then we also combined this with a high-level description language for finitary initial epistemic theories. That is a subset of possible theories that we can deal with, that allows us to reason about the effects of sequences of actions and plans by updating only one single multi-pointed epistemic model. More details at the poster presentation and or in the paper. Thank you very much.